Hi viewers, welcome to my channel. So in today's class, we're going to continue with our lesson on dimension analysis. And today, I'm going to show you how to find the dimension of a constant. So before we proceed, I would like you to subscribe to my YouTube channel. Also press the notification button so as to receive every new video I'm going to be dropping on my channel. So let's consider this example given here. So the first example says we should find the dimensions of the gas constant R given that PV equals to nRT. This equation given is regarded as ideal gas equation, and we can also call it the general gas law. Now, this particular equation evolved as a result of the combination of the three gas law, that is the pressure law, the Boyle's law, and the Charles law. And let's consider these three equations. What does the pressure law say? The pressure law states that the pressure of a fixed mass of gas in an enclosed system is directly proportional to the temperature provided that the volume of the container is kept constant. Mathematically, P is directly proportional to T. This implies that P is equals to KT. If we consider the constant given here, our K will be equals to P over T. Let's call this equation 1. And what does the second gas law says, which is Boyle's law? Boyle's law states that the volume of a given mass of gas is inversely proportional to the pressure provided that the temperature is kept constant. That is, V is inversely proportional to P, which is pressure. This implies that V will be equals to K over P. Considering the constant, K will be equals to PV. This is regarded as the equation 2. Now, the third law, which is Charles' law, states that the volume of a given mass of gas is directly proportional to its absolute temperature, provided that the pressure is kept constant. Mathematically, we can express this as V to be directly proportional to what? To temperature. This implies that V will be equals to KT. Considering the constant, K will be equals to V over T. This is equation 3. So if we equate these three equations given to us here, we're going to be having K to be equals to P over T to be equals to PV equals to V over T. And our constant will be given to be PV over T. PV over T. And this will be expressed as P1 V1 over T1 equals to P2 V2 over T2 equals to Pn Vn over Tn as the number continues. Now, given that PV equals to nRT, where P, let's interpret the parameters given to us. P is the pressure, P is regarded as pressure, and V is regarded as volume. The N given here is called the number of moles, number of moles, number of moles. And the R given here is considered to be the universal gas constant. Universal gas constant. And some people call it ideal gas constant. Gas constant. Where T is the absolute temperature. Absolute temperature. Now let's find the dimension of the constant R. So the first thing we need to do is to make R the subject of the formula. Given that PV equals to what? nRT. All we need to do is to divide both sides by what? By NT. We divide both sides by what? By NT. So that R will be equals to PV over NT. Now let's find the dimension of this constant here. We recall that pressure, the dimension analysis of pressure is given to be ml raised to the power of minus 1 T raised to the power of minus 2. And the dimension of volume is L raised to the power of 3. We have done this in our previous class. You can check out my video on dimension analysis where we discuss the dimension of work, power, pressure, etc. Now we proceed. The N, which is the number of mole, the symbol of number of mole is given to be mole, and the temperature is K, which is Kelvin. Now, if we integrate this particular dimension here, we also have to recall our knowledge of indices, which is product law. That is M multiplied by L raised to the power of minus 1 multiplied by L raised to the power of 3 multiplied by T raised to the power of minus 2 over mole Kelvin. Now, for the product law, the power now we're going to add it up, and we're going to be having ml raised to the power of minus 1 plus 3. Minus 1 plus 3 is going to give me 2 multiplied by T raised to the power of minus 2 over mole Kelvin. And we can re-express this as ml raised to the power of 2 T raised to the power of minus 2 mole per mole. We have this one to be per mole per Kelvin. Per mole per Kelvin. And from this dimension, we can also derive the unit of this constant to be joule per mole per Kelvin. Now, I know you'll be wondering, where did we get this joule? I need you to recall that pressure equals to force over area, and the unit is Newton per meter square. Newton per meter square. Now, from this expression here, if we integrate this and we multiply it with the dimension, with the unit, and we multiply it with the unit of the volume given here, we're going to be having pressure multiplied by volume. This will be N over M square multiplied by M raised to the power of 3. Now, if we cancel out this now, we're going to be left with Nm. And Nm is equals to joule. Nm is equals to what? Joule, as work done is equals to force times distance. The unit of work done is given to be Newton meter and also joule. But we used all these units in different cases when solving question in physics. Therefore, the dimension of the constant is given to be ml raised to the power of 2 T raised to the power of minus 2 per mole per Kelvin. That is the dimension of the constant R. Now let's consider other examples. The second example says that we should find the dimensions of the gravitational constant G, given that F equals to G m1 m2 over r square. Now this particular equation is derived from a law called Newton's law of gravitation. Newton's laws of gravitation. And Newton's law of gravitation states that the force of attraction between two bodies of mass m1 and m2 is inversely proportional to the square of their distance r. Is inversely proportional to the square of their distance r. That is, if F is directly proportional to m1, m2, let's consider this to be 1. F is inversely proportional to what? To distance r square. Now we can integrate this and we're going to be having F to be equals to K m1 m2 over r square. Now let the K to be equals to G, gravitational constant. So F will be equals to G m1 m2 over r square. Now let's find the dimension of the gravitational constant G. All we need to do is to make G the surface of the formula. So let's do that now. G m1 m2 will be equals to fr square. Divide both side by m1 m2 m1 m2. So G will be equals to fr square over m1 m2. So now let's find the dimensional analysis of the gravitational constant G. We recall that the dimensional analysis of force, you can check out my video on that. The dimensional analysis of force is given to be ml t raised to the power of minus 2 Now let's integrate it here. G will be equals to ml t raised to the power of minus 2, the dimension of the radius, which is L squared, over m times m. Now we can have mlt raised to the power of minus 2 L raised to the power of 2 over m squared. So we can proceed by saying m L raised to the power of 1 plus 2 t raised to the power of minus 2 m raised to the power of 2. So if we apply our knowledge of indices, that is m raised to the power of 1 divided by m raised to the power of 2, this is going to be m raised to the power of 1 minus 2, and this will be m raised to the power of minus 1. So we can say L raised to the power of 3 t raised to the power of minus 2 over m. Therefore, the gravitational constant G will be given to be m raised to the power of minus 1, L raised to the power of 3, t raised to the power of minus 2. So the dimension of the gravitational constant is going to be m raised to the power of minus 1, L raised to the power of 3, t raised to the power of minus 2 will be the dimension of the gravitational constant. Now let's consider the third example. The third example says we should find the dimension of the Planck constant given to be h, given that E equals to hf. So this particular equation is derived by a scientist called Max Planck. Max Planck. So all we need to do here is to make h the subject of the formula. That is, given that E equals to the Planck constant f. So h now will be equals to E over f. Recall that f equals to inverse of what? Of time t. So let's consider the dimension of energy E. The dimension of energy E is given to be ml raised to the power of 2 t raised to the power of minus 2. So let's substitute this dimension into this expression, that is h will be equals to ml raised to the power of 2 t raised to the power of minus 2 over t raised to the power of minus 1 over t raised to the power of minus 1. Now we can integrate this. By integrating this, we recall that t raised to the power of minus 2 divided by t raised to the power of minus 1 can be re-expressed as t raised to the power of minus 2 minus minus 1. And this is going to be t raised to the power of minus 2 plus 1. And t will be raised to the power of minus 1. Therefore, we can re-express this and say the Planck constant equals to ml raised to the power of 2 t raised to the power of minus 1. So this will be the dimension of the Planck constant given to us. And from this place, we can also determine the unit of the Planck constant to be kilogram meter square per seconds. Kilogram meter square per second. So this is the dimension of the Planck constant given to us. So if you like my video, kindly subscribe to my YouTube channel, share with friends, and press the notification button to receive new video. See you in our next class. Thank you. Bye.